Hello, my name is Victor Veliadis, and together with my co-PIs, Dr. Iqbal Hussain and Dr. Subhasis Bhattacharya, we've been working on the VTO project titled Rugged Wide Bandgap Devices and Advanced Electric Machines for High Power Density Automotive Electric Drives. The timeline of the project is 5 years. The total budget for the 5 years for NC State is $1.5 million. So about 300K a year. And the barriers and technical targets are a high power density for the machine to be equal or higher than 50 kilowatts per liter. We want the peak power of the machine to be 100 kilowatts. We want the cost to be $3.3 per kilowatt or less for a heavy rare earth free design. And we want the GaN devices to be basically tested for reliability and ruggedness and ultimately qualified for automotive applications. Our partners in the project from the national labs are Oak Ridge National Lab, NREL, Sandia, and Ames. So a brief introduction of the relevance and objectives. As I mentioned before, we're looking for a power density of 50 kilowatts per liter for a 100 kilowatt traction machine that is heavy rare earth free. We want to bring the cost of the machine down to $3.3 per kilowatt, and we want to basically test and qualify GaN devices for electric vehicle operation. So in the 2019-2020, the first budget period, we completed the design of 3 different machines. We did an analysis and down-selected topologies that meet the target of the project. We evaluated the ruggedness of the commercial wide bandgap devices in terms of short-circuit performance, avalanche energy, surge current, their resistance, and also we determined their safe operating area. And we also looked at short-circuit and inductive load performance of commercially available GaN devices in order to develop gate drives for short-circuit detection, voltage clamping, and basically robustness under high DVDT operation. The goal is over the next few years to have the test sets ready and the circuit knowledge in place to evaluate devices, GaN devices that will be an outcome of this project. What is the overall impact? We want to accelerate the development of GaN devices and electric machines for electric vehicles to improve fuel efficiency and cost. So the milestones for the first phase: evaluate devices, design different machines that meet the spec, and analyze, down select the best machine to move forward with. And in the second phase of the program, we will work on gate drives based on the information we have from characterizing commercial GaN devices. We will optimize the 100 kilowatt electric machine, and the requirements are shown at the table to the right. We want the cost to be $3.3 per kilowatt or less. We want the power density to be 50 kilowatts per liter or higher, and the system peak power is 100 kilowatts. So I will start with presenting work on the wide bandgap device evaluation. And this is the portion that Professor Subhasis Bhattacharya is involved in and has carried out the work. So we have done modeling and looked at the losses of devices. We've selected commercially available devices for testing. We've looked at their ruggedness and evaluated through double pulse tests, short circuit tests, and power cycling to look at their stability. And we've also determined the safe operating area of tested devices by using measurements and values that appear on their data sheets. So we basically compared GaN-based devices in an inverter. So we also use silicon carbide devices that are very extensively being evaluated and worked on through other performance of this project. and we assumed an 800 volt DC bus, which is the higher voltage that electric automotive engineers are moving to. In the case of silicon carbide, the devices are rated at 1200 volt, so we use the two-level topology. In the case of GaN, the commercially available devices are rated at 650 volts, so then we did a three-level in order to implement the 800 volt DC bus. And you can see to the right some graphs of their comparison. As is well known, the GaN has a very big advantage with respect to switching frequency. It can operate at very high frequencies. So as you can see, the switching losses for the GaN devices or the GaN inverter topology are calculated to be a lot lower than what they would be, than what they are for silicon carbide. And that's because they're able to operate at higher frequency, have faster switching. This analysis, of course, was done for 800 volts. And the comparison between silicon carbide and GaN is to have the silicon carbide as a reference point for the work that we do for the GaN. So the first thing we did is we looked into the losses of the silicon carbide and GaN devices, and we showed before that the GaN inverter, the three-level, has lower losses. And based on the losses, we did some calculation to estimate the volume of the heatsink. So the parameters for the calculation for the two-level silicon carbide-based inverter and the three-level GaN inverter are shown on the tables to the left and the right, respectively. And from our calculations, we've basically concluded that we can implement the GaN inverter with a 3.3 lower volume in heatsink. So the heatsink gets reduced 3.3 times in volume, and that of course is due to the fact that at the higher frequency where we did the switching loss and conduction loss calculations, GaN does perform extremely well. The second thing that we did is we looked into designing a DVDT filter. As we know, widebandgap devices have very high DVDTs. So we use the NEMA standard for motors rated under 600 volts that says that the DVDT should be below 1600 volts per microsecond. And we developed a filter, an LC filter, to do this. And assuming that both in the case of the two-level silicon carbide system and the three-level GaN inverter, the capacitance is the same. In the case of the GaN, we have an inductance that's about 4 times lower. So that makes for a cheaper, lower volume, and less expensive LC filter in the case of the GaN. And that also has to do with the fact that the GaN has is using a three-level topology versus a two-level for the silicon carbide. The next thing we did is we looked into the short circuit capability, and we ran some short circuit measurements. Short circuit is very, very important. For silicon, it's 10 microseconds. In the case of GaN, unfortunately, and this is also well known, the short circuit time is extremely short, and the avalanche capability is very, very small, or even not supported at all. So basically, through running these measurements, we determined that the short circuit basically times are in the hundreds of nanoseconds, or even less than 100 nanoseconds for GaN, and that means that we have to have a gate drive that will detect a short extremely fast, and we'll be able to shut down the circuit extremely fast as well. So we also did stressing type of experiments. So we did thermomechanical stressing by doing 8,500 power cycles, and we measured, of course, the parameters like threshold, RDS, and so on and so forth before and after the stress to evaluate the impact of stressing on the devices and the overall reliability. So we have the setup for this type of degradation measurement as well. Finally, through the measuring the RDS of the devices and looking at the pulse current rating and junction to case thermal resistance from the device data sheets, we were also able to determine the safe operating area of the device, which is very useful for designing circuit protection. Okay, so just very briefly, the remaining challenges and barriers for GaN devices. They have a very low short circuit time, particularly when compared to the prevalent silicon technology. So we need to develop techniques where we can do very fast fault detection and isolation. We need to develop over voltage protection, and of course, they're wide bandgap. GaN is a wide bandgap device, so it has a very high dVdt. So we need to design filters for that. So optimize gate drives, and then we also need to look at the current sharing, because the these applications call for very high current levels, and wide bandgap devices, because of defects in the wafer, tend to be smaller in area. So a number of them have to parallel to get to the high current levels. And the final step is to optimize the GaN inverter design. Okay, so with that, I will move forward with the machine design evaluation, which is the other aspect of the work that we do. And in this first year, we analyzed 3 types of heavy rare earth-free PM machines. We did this using electromagnetic finite element analysis. So design 1 was a permanent magnet with stranded conductor in stator. The second machine that we had was a permanent machine with space-shifted Y delta winding. And the third design that we looked at was a slotless holdback PM machine with integrated in-teeth cooling. So in all 3 designs, there were several innovations that were included in the segmented rotor, the windings, and the outer rotor for the holdback arrangement, and the in-teeth cooling. We used advanced materials, and of course the designs had to meet the maximum power of 100 kilowatts and the continuous power of 55 kilowatts, and FEA was used to do the analysis of the different designs. And based on this analysis, we have information to optimize and down select a machine in year number 2. So the first design is the machine with a stranded conductor in stator. It's got several innovations, and it's got use of advanced materials. There are no heavy rare earths. We're using ultra-conductive copper conductors, Cooltherm, and hypercore. And doing the finite element analysis, we can see that this machine does meet the peak power of 100 kilowatts, but it doesn't get us to the 50 kilowatts per liter as far as the power density is controlled. So further optimization is needed. And you can see to the right the power versus the speed for peak power, continuous power, and then peak torque and continuous torque. And also we're looking at the torque as a function of the rotor position. The second machine we tested, it's a PM machine with space-shifted Y delta winding. Again, there are innovations in this machine, like a segmented magnet design, ultra-conductive copper conductor, and winding cooling, and space-shifted Y delta winding. And we use, again, similar advanced materials, and of course it's heavy rare earth free. Doing the analysis on this machine, we find that the peak power is met, and also the power density is at 48.5 is very close to the 50 kilowatt per liter that we're looking by the end of the program. And to the right, we have similar graphs as with the other machine, looking at the peak and continuous values of the torque and the power. Finally, the third machine that we designed is a slotless holdback PM machine with integrated in-teeth cooling. So enabling innovation technology on this one, we're using an ultra-conductive copper conductor. We have a double layer stator winding holdback rotor that's on the outside, and integrated in-teeth cooling. We use the advanced materials that we used for the other designs, and the advantage of this machine is that the drive, the inverter drive, can be integrated in the machine, okay, which of course is very beneficial, but it does create thermal management challenges. So if you look at this machine, it's got integrated in-teeth cooling. We've introduced cooling channels through the non-magnetic teeth of the slatted stator. There's a second cooling path used beneath the stator yoke. The second cooling path provides a parallel path for the cooling, and this thermal system can also be used for cooling the integrated drive. And there's a schematic drawing of the cooling system on the machine. So, having evaluated 3 different types of machines, this slide summarizes their performance, their parameters, and if you look at the peak power, all 3 designs are meeting the 100 kilowatts. The power density, however, is below the 50 that's required on designs 1 and 2, and design 3 has shown a path to 50 kilowatts. However, all 3 of these designs are good candidates. So in the second year, we'll continue some optimization of these designs before we down select one design to move forward with and actually fabricate and test. So the barriers that we have to overcome is the magnetization at elevated temperatures, the thermal performance, thermal management in the entire operating range, and of course we're using advanced materials, so the availability of some of these bulk materials and their structural performance at the maximum speed also need to be looked into. And the proposed future research is to do electromagnetic finite element optimization of the different designs, and particularly design 1 and design 2 that have not met the power density, the 50 kilowatts per liter power density requirement. And moving into FY 2021, we want to do a comprehensive demagnetization check for the HRE-free magnets for the 3 designs. We want to perform comprehensive thermal analysis on the 3 designs to meet the continuous operating temperature requirement at about 150 C. We need to perform structural analysis on the 3 designs for high-speed operation, giving us acceptable stress limits, and then we'll down select one machine with the best potential to meet power density and cost targets. And once we down select the machine, we will actually fabricate the actual machine and test. So with that, I will summarize the work on the electric machines. We tested 3 PM machines. They all contain innovations in the design as well as in the materials that are being used. In this first BP1 phase, we used finite element analysis to evaluate the designs, and we found that the maximum power of 100 kilowatts is met, and the continuous power of 50 kilowatts is only met by one of the designs, so optimization needs to happen with the other designs before we down select. And in all these designs we're using advanced materials, and they're all heavy rare earth free. And we basically analyzed the electromagnetic results, summarized them, did some comparisons between the machines, and basically our work showed that all 3 designs have the potential to achieve the target goals with some optimization. And that's what we'll be doing in this next budget period. We'll work on further electromagnetic optimization analysis, and we'll also do some thermal and structural analysis. Thank you so much.